Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at additional topics in approximating the solution to a system of linear algebraic equations, or as you'd say in linear algebra, a system of linear equations. So in this topic, we will review what has already been covered, specifically Gaussian elimination with partial pivoting and the Jacobi method. We'll describe what we will cover in this topic, including the Gauss-Seidel method and the method of successive over-relaxation. And we will conclude by reviewing an implementation of the Jacobi method in MATLAB. Now, we have already seen how we can use Gaussian elimination together with partial pivoting and backward substitution to reasonably approximate the solution to a system of linear equations. And again, we say approximate because we are always using double precision floating point numbers, which inherently have errors associated with them. We've also seen the iterative Jacobi method. Now, this method is only useful when the matrix is strictly diagonally dominant. Now, what that means, I'll quickly review, is that the absolute value of each diagonal entry is greater than the sum of the absolute values of all other entries in that particular row. Looking ahead, we're going to see two additional techniques, the Gauss-Seidel method, and this is simply a modification of the Jacobi method, and the method of successive over-relaxation. And this is the idea of pushing an approximation ahead in the same direction that it is already going. Let's now review the Jacobi method implemented in MATLAB. Suppose we are solving a times u is equal to v, and u is the current approximation. Well, we're going to iterate a maximum of max iteration times, so we have a for loop running that often. We're going to store the current approximation in a variable called uold, the previous approximation. We will then update the current approximation u. So we're going to update each entry of u individually. So we have a loop going from 1 to n, and thus we start by assigning the ith entry of u the ith entry of the target vector v. We then subtract off the off-diagonal entries of the ith row of A multiplied by the corresponding entries of the old vector from the previous iteration. And we're going to do this for each entry of u. Finally, we divide the ith entry of u by the diagonal entry of the matrix A. Okay, having done that for every single entry of the vector u, we then check, is the distance between the current approximation of u and the previous approximation of u, is that norm less than epsilon step size? And if it is, then we will return. And of course, this is going to return the vector u. So following this topic, you now have reviewed what we have seen so far with respect to solving a system of linear equations. First, Gaussian elimination with partial pivoting and backward substitution, and the Jacobi method. And you understand the two next topics we will cover, the Gauss-Seidel method and the method of successive over-relaxation. We've also reviewed an implementation of the Jacobi method in MATLAB. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!